All right, welcome everybody. Thank you for coming out today. I have the highly desired after lunch slot, so I'll try to keep you guys awake as much as possible. So first, I wanted to start off with a little survey. How many pen testers are in here today? Just raise your hand. Okay, good number. Network security background? Raise your hand. Application security? Okay. Now, are you now or have you ever been a developer? All right, that's good to know. What about managers, managerial roles? Got a few? All right, well the good news is that this is going to apply to all of you. So more so to the developers, but really it applies across the board because it's about how to change the behavior of the development organization. So yesterday we heard about a lot of the new security features of HTML5 and some novel attacks on that. Today we're going to focus a little bit more on the development side of things, how you as a developer or as a development organization can really make a difference in the quality of the software that you produce and how that affects security. So here's a quick overview, and I'm going to just jump right into the introduction. And then cover some software security basics to make sure everybody's on the same page. And we're going to talk about some common application vulnerabilities. Now, hopefully none of these are going to be news to any of you. What's important here is to focus on how we fix that. What can we do to actually not just address to kill the exploits, but the actual root cause, the vulnerabilities that lead to these exploits. And we'll show some code examples. And then we'll take a step back and talk about how can we build this into the software development lifecycle at the organizational level, at the process level. So just a few words about Cigital. I work for Cigital, which is a software security consulting firm. We were founded in 1992, which is a good while ago in this industry, certainly. And we started on the software quality side, and we've now moved into software security, and almost 95% of what we do is application security, software security, whatever you want to call it. And we've written a lot of books, yada, yada, yada. Not me personally, all the other sharp guys at Cigital, like Gary and everybody else. So they're doing great there. So, and I know there's a couple of former or current developers in here, so no offense, but why are most programmers bad at security? Well, it's simply not part of their job description. They are not, they're focused on very different things than security professionals. They're usually under time pressure. They're focused on adding new functionality, adding new features, and the incentives are not there to really help them be successful at creating reliable, secure software. A lot of times, design of a system and development of a system is very much focused on the positive path, the if statements, not the else statements. What is the expected behavior? And a lot of times when I tell a programmer, okay, well, you've got this vulnerability here, and an attacker could type something in here. Well, our users wouldn't do that. That's not how it's designed to be used. So there's a lot of focus on what the expected behavior is versus what some alternate ways are of abusing the system. And really the bottom line is that input validation is much harder than it looks on the surface, especially doing it the correct way, which is whitelisting, and I'll talk some more about that. So basically what we have right now is that most of what qualifies as IT security is actually bolted on way late in the development cycle. It's pen testing just before go live. It's slapping a firewall in front of it, slapping an IDS in front of it, just to see if you can catch some of the things. But it really doesn't address the underlying problem. So what you end up with is you have short-term protection that's sort of limited in scope. So a better approach is to really think about security from the beginning, to build it into your development lifecycle. So you start with security requirements. You ask the right questions during the requirements gathering phase. You ask the business owners, what is this software designed to do? What are the security implications of that? Are we storing any sensitive data? And all of those types of things. And then you bake that into your design, into your architecture, and into your code eventually. And then, of course, you test it as you would any requirement. And so what you get with this approach is robust, long-term security, because one of the things that, a lot of times developers don't think about it this way, but you actually have a lot of power, because you as a developer are creating the rules of engagement that any attacker has to play by. If you design a lockout mechanism and you do it the correct way, the attacker won't be able to get around it. They're going to have to play by your rules to get into your system. So there's actually quite a bit of power that the developer has. These are the 7 areas where things most likely will go wrong in any particular application. I've already mentioned input validation. There are multiple different ways of representing input in any context. Think about URL encoding, HTML entity encoding, all these different ways of representing data, Unicode, all these different things. So API abuse is another one. So having, this again comes back to our users wouldn't do that. APIs are often designed for one thing, but they can also be called by other third parties, by other people that they weren't designed to be called by and used in different ways that are unexpected. Security features can actually be a detriment if they're not implemented correctly. And of course, there's time and state, race conditions, temp files that are created that can lead to issues. We have standard error handling, can either be too verbose or it can ignore some failures silently that just that lead to unexpected behavior down the road. Standard code quality issues, memory leaks, things like that, and encapsulation, having strong boundaries between your data inside the application. In the case of object-oriented programming, having the correct private variables and so forth. So here's just a quick recent example of APIs, and this has become more of an issue as web services have become more popular, because as we heard yesterday, most Twitter, Facebook, they're all accessible both via the front end and via the API. And a lot of times, if those two are not in sync, if the security mechanisms are not consistently enforced across those two, you can end up with issues that an attacker can abuse. So I know a couple of years ago, Yahoo had an issue where they were not enforcing a password lockout on their API. So if you went to the Yahoo front page and you tried a whole bunch of different passwords, you would get locked out after a few attempts. But if you did the same thing via their API, you could bang away as long as you wanted to, and people were actively exploiting that to crack weak Yahoo account passwords. So now we're going to dive into the vulnerabilities. And again, these are all well-known vulnerabilities, but the focus here is on fixing them. And I'll just give a brief description of each of them to make sure everybody's on the same page. And a lot of this material is, OWASP is a great resource for anything application security, software security related, and they have a lot of good resources there. So we're going to talk about unvalidated input, injection flaws, cross-site scripting, cross-site request forgery, what the difference is between those two, improper error handling, broken access control, and insecure storage. So can anybody tell me, just shout it out, does this look like a good idea? Does this look like a good way, everybody can read that? Does this look like a good way of taking an input parameter? And if not, what could be the possible issues here? Go ahead. Exactly. So that's exactly one of my examples. An attacker, if you're not validating this correctly, they can actually access internal hosts on your network right through the the public-facing web server, potentially. Or they can use it to browse files that are present on the local server where that application is hosted. So it's very important to think about what the intended use is of that code and to validate that input accordingly. So thank you for that. It was almost like I planted you in the audience. So what do we do about it? Well, actually, first, let me take a step back. First, we have to realize that, and most of you, I'm sure, already know this, but the attacker can tamper with any part of the query string. Talking about the URL itself, the query string, anything that's part of their initial request coming in, headers, cookies, it should be considered tainted, untrusted data. And of course, there's a whole long list of attacks that rely on poor input validation. But usually it comes down to two things. Either filtering is implemented as a blacklist, or the input validation, and believe it or not, we still see this all the time. It sounds so obvious, but a lot of times input validation is either only performed at the client or it's inconsistent. It's not, the same validation is not performed on the server as on the client. And some people still think that a drop-down or a bit of JavaScript is a good way to perform input validation, which is great from a UI perspective. It makes it easier to use, but it has no security value. So this is a bit of a dated example from '09, but I just love it, so I wanted to point it out real quick. Time Warner Cable had these neat little boxes that they would give all their customers, 65,000 of them, and it used JavaScript to hide admin functionality. Turned out that if you just disable JavaScript in your browser, you could then see the admin functionality without any password. And even better, you could download the configuration file for the router. But wait, there's more. It had the plain text admin password and username and password in it, and it was the same hard-coded across all of the devices that they deployed. So I mean, this was out there just a few years ago, and I'm sure it still is today. So we keep seeing the same mistakes over and over again. And yeah, here's a little description of what happened there. Okay, so what can we do about it? As a developer, as a development organization, what can we do about it? All input needs to be validated on the server, and it should be done by whitelisting. So there's a couple of different things that you want to check, and only if that input passes all of those checks should it be allowed to proceed. So you can check things like the data type. Are you expecting a string, a date, an integer? Check the minimum and maximum length, and whether, for example, whether or not a zero, a null value, or blank value is allowed. And if it's a number, check the numeric range to make sure that it's within whatever the expected value is. And of course, a lot of this falls under this last category, which is there's well-known data formats, phone numbers, zip codes, dates, email addresses. Those are easy. They have a known format. You can whitelist validate that with a regular expression. And if there's anything extra in there, you reject the input. Whatever you do, do not strip out anything. Don't try to look for bad characters and strip them out. There's all kinds of ways that can go wrong and that can get abused. So always just, if there's anything unexpected, if it doesn't pass the regex, just throw an error. And don't abuse hidden fields. There should be one cookie that your web app uses, and that's the session cookie. That's it. Don't store anything else in hidden fields, cookies, anywhere else. Store it in a session variable that lives on the server that the attacker can't mess with. And so here's a quick Java code example, very simple, about how to do date validation. So you can see, first, we've separated out the validation logic. So that's just from a OO design perspective is a good idea. And it might be a little hard to read because it's gray, but it's at the bottom here. You can see the regular expression. It starts with a caret, which is important because that means match the beginning of the string. So if there's any extra characters at the beginning, it's not going to pass. And it ends with a $, which means match the end of the string, and so forth. And so 4 digits, dash, 2 digits, dash, 2 digits. So standard SQL year, month, day format. And only if it matches, return true, and otherwise throw an exception. And obviously, error handling should be done via exceptions, not via true, false, return values, and so forth. So simple example, but you'd be amazed as how many people still get this wrong day to day. So moving on to injection flaws. So of course, the most well-known of these is SQL injection. And this, again, is a very simple PHP example where a query is being built from string concatenation to user-supplied variables. All the attacker has to do is enter admin, single quote, or 1 = 1, comment out the rest of the query, and sure enough, they change the structure of the query, and now you're no longer in control of your database command because they can now inject anything they want. And so obviously it'll authenticate in most cases, and sometimes you even get lucky and it dumps the entire contents of the user table and you get a list of all the valid usernames. So in general, injection flaws can really occur anywhere where there's an interpreter involved. So that can be Perl, Python, JavaScript, of course SQL. Anytime you have an external shell that it's calling a command shell, if you're doing operating system calls, database systems, and of course path traversal when you're calling, when you're building strings to access system files. So I'm going to use a few screenshots. There was a recent web app pen test that I was involved in, and we found a single command injection vulnerability in a third-party toolkit, image processing toolkit. And this allowed us to run shell commands unprivileged as the web server user, essentially, the Apache user. But eventually, we were able to use that through a sequence of events. We were able to use that to gain admin access, shell access to the server because of some other configuration mistakes that they had made. So I'm going to use a couple of screenshots from this to show some examples. So here's the first example. It's probably really hard to read, but basically in the URL up top, I injected ls-lh right just by appending a semicolon and then ls-lh, and also cranked up the debug level to 9, the highest value. And so we can see the result here that it shows the ls output there, and we were able to use that, and I'll show another example later of how we got additional access from that. But it's basically just, it's poor design. They weren't validating the parameter correctly. They were expecting a number, but they allowed me to put in an entire command string there. So what can you do about injection flaws in general? You want to try to avoid external interpreters whenever possible. So for example, in the Java world, if you're trying to send mail from inside a Java program, don't use runtime.exec to call send mail. Use the Java Mail API instead. Always make sure that you encode special characters before you send it to the back end, and that depends, of course, on what you're sending it to. Semicolons and backticks are sensitive in the context of shell commands. Single quotes, obviously, in SQL statements. But for that, it's actually better to use parameterized queries, and we all know how that goes, and I'll show a quick example on the next slide here. Very important to run the external application with limited privileges. You may want to have a separate account. You can run it under the web server user, but it's probably a better idea to have yet another separate user account just for those backend applications that can't access anything else, very limited privileges. Make sure that you check all the output, return codes, and error codes from the third-party application so that if there's anything unexpected, you stop, you throw an error, and don't proceed. So here's a very quick example of a PHP parameterized query, or what they call a prepared statement. And so again, you set up the structure of the query. This is the same example that I showed before. PHP has a kind of a neat feature where you can actually name the parameters. It's not just positional. You can actually assign different names to them. And then you call the two bind functions there. You bind the values to them. And then you execute the statement. And it's really as simple as that. And when you're doing that bind, it automatically knows that anything in that string needs to be escaped. So you see at the bottom here that it actually puts a backslash in front of the single quote, which means it's just part of the string. And so that request would obviously fail because there's no user that's named admin single quote or 1 = 1. And I mentioned OWASP. They have a lot of these great resources. They call them cheat sheets. They have it for Crosssite scripting, for SeeSurf, for query parameterization. So there's a link to it. They have examples in probably a dozen different languages of how to do this in your environment. So just a quick reference makes it easy. So we hear a lot about Crosssite scripting and Crosssite request forgery. Most of you are probably familiar with it, but I'm just going to cover the differences real quick and to kind of show how they relate to each other. Crosssite scripting injects content into an existing page, while SeeSurf takes an action on behalf of the user that's currently logged in. Now, XSS can often be used to launch SeeSurf, and it makes for a much more powerful SeeSurf attack once you have crossed over into that trust boundary and you're in the same code base as the native JavaScript. So here's two quick examples, pretty straightforward. Cross-site scripting, posting a comment, for example, to a message board and injecting some script tags into that. And here is an example of adding a friend, adding the attacker as a behind the victim's back, so to speak, adding them as a friend on their social network so they can see their contacts. So cross-site scripting, basically the attacker injects malicious code into the web page, it's sent to the browser, and the browser basically just assumes that that code is part of the web page and runs it. And that script now has access to any of the same cookies, session tokens, anything else that's stored in that context for the domain. We've got reflected and stored cross-site scripting. On the other hand, SeeSurf, so another way of looking at the difference between these two is to say that Crosssite abuses or misuses the trust of the user in the application, while SeeSurf is the other way around. It abuses the trust of the application in the user because it thinks that the user is actually taking an action that the user didn't intend to take. And cross-site scripting misuses the trust of the user because they think that the functionality that they're seeing is built into the web application, or they may not see the functionality, but it's really not intended to behave that way. So Crosssite SeeSurf is a good example of SeeSurf is basically making an unauthorized request on behalf of an authenticated user, such as initiating a bank transfer without them being aware of it. So, the simplest way to launch SeeSurf is just to put a link in an image tag, and when that image is loaded, the get URL is accessed, and that's easy to defend against. More sophisticated SeeSurf attacks that are very difficult to defend against are the ones that are launched via cross-site scripting, because then now you have full sort of interactive programming ability. You can make a get request, you can get the token back, you can post the token with the next request, so it makes it a lot harder to defend against that. So again, what can we do about it? This is really what it boils down to. Again, I'm going to say it again, input validation. If you do your input validation right, and if you do a whitelisting, then it's going to stop most of these attacks. Just in case you missed something, you want to also use output encoding as a fallback. And this is going to be dependent on the context of where you're putting this output. If you're putting it into a HTML context, there's going to be different encoding than if you're putting it into a JavaScript or a CSS style sheet context. And for example, jQuery has an encoder library that does that, has different functions you can call to do exactly that. SeeSurf prevention, as I mentioned, is a little bit trickier because you can prevent the simple attacks just by using a token, so that every form has a unique value associated with it, or every request actually has a unique value associated with it, and if that value is not included in the next request, then you just discard the request. But it doesn't help you if the attacker is actually exploiting another vulnerability, such as cross-site scripting, to get inside the application. So really, the strongest defense, and this is very much dependent on what you're trying to defend. If it's a sensitive transaction like a bank transfer, then you would probably want to go to this length to make sure that it is the user who is intending on performing this action. So you can do things like CAPTCHA, which we all know has some issues, but it's nonetheless effective. If you want to go even further along the spectrum, you can reprompt the user for their password. And again, you would only want to do this obviously for in the cases where it's a very sensitive transaction. And of course, you can use something like a one-time password, secure ID, to basically do a per transaction authentication. And here is, it's actually a very short example. It's basically a one-liner. If you're doing in ASP.NET, it has this built-in mechanism called ViewState, which was never really designed as a security feature, but it's designed to track form values across different requests. And it checks automatically, by design, the framework checks the integrity of that cookie with every request. And so if you simply set the current session ID to be the key for the view state, then it will automatically perform this validation for you. So it's great in the sense that you don't have to have any external libraries, you're not making any major code changes to your application, but there's a few issues with it because this requires you to put basically a code hook into each page. This is done on a per page basis. And so it's easy to forget to put one in there, especially if you have a big web application. And it's even more of a pain to audit and having to check this across the application. And the developer can either intentionally or unintentionally disable this feature. And then there's also some issues with load balancing because the session IDs are not always replicated across the servers. So it's a great sort of quick and dirty solution that's going to get you 80% of the way there, but it's not sort of the best solution. So OWASP has 3 projects that are all related to each other that are SeeSurf Guard in .NET, Java, and PHP. And what this does basically is it allows you to handle this token management, creation and checking of the token transparently to the programmer and transparently to the user. So you can handle it, you basically set up a central configuration file that hooks into the web server, and then with every request, it figures out whether or not it needs to include a token, it puts the token in there, and then it checks it on the following request. And there's a link in here to OWASP for more information. So improper error handling. So if you have, if you're giving the attacker too much information in an error message, that can really give them a lot of clues about how to attack your application and how to mess with it. And so examples of this, obviously, stack traces, database dumps, specific error codes for Java, JSP compilation errors that may have full paths in them. If you're giving an inconsistent error message, access denied versus file not found, or invalid username versus invalid password, and so forth. And of course, denial of service. And also, you always have to watch out with error messages. If you're repeating any user input back to the user, that can lead to a reflected cross-site scripting attack because it might allow, if you're not validating it, it might allow the user to inject input content there. So how do you handle this? You want to make sure that in your application you're defining clear and consistent error handling. A centralized error handling mechanism is usually the best approach. You want to make sure that you give the user short but meaningful error messages that are actionable. And you want to log more detailed information on the back end that only the admin would be able to access. So you don't want to give useful information for an attacker, stack traces, detailed exceptions, that sort of thing. And you want to make sure that you're catching specific exceptions and handling them as best as you can within the application logic. Don't just catch everything at the top level and throw a generic error. But you do want to make sure that as a fallback, you put a general catch block at the very top level so that if you missed anything, that it gets caught there and you don't end up with a stack trace. It's also a good idea to modify the default error pages that your web server defines. So another issue that we see a lot is that access control is not applied consistently. And this comes back to what I was talking earlier about the ViewState, because a lot of times access control is implemented with code hooks. So if you forget one of those, then 99 of your pages might be okay, but there's one out there where the programmer just forgot to put the authentication check into it. So there's insecure IDs. If you can guess sequential numbers of some sort, if you know a particular URL, you might be able to force browse past that. Path traversal and client-side caching can also be an issue if you don't disable caching for sensitive information. So as I mentioned, homegrown authorization schemes are usually not a good idea because it can lead to exactly that issue of missing one particular page or one particular part of the application. And so here's a good example of, this was part of that same pen test that I mentioned earlier. If you just went to server name /logs, you could actually see a copy of the access log and the error log from Apache there. Which would disclose, all of the IP addresses that have accessed that server. You could see all the different URLs that were valid on that server that you may not have known about otherwise. So it's really a goldmine of information for an attacker. So what's the mitigation approach here? Access permissions should be checked with every request. And so you want to make sure that it's consistently applied, that there's not a chance of missing one of these access control checks by doing it in a centralized way, which is easy to do if you don't roll your own access control. So for example, on the Java side, Spring Security has a wide range of features that let you define how you want to perform authorization checking, and it's declarative instead of programmatic, so you're not relying on putting code hooks in, you're managing it all in one place. And then other things to look out for is you want to make sure that you're using HTTP headers to set the caching behavior for sensitive information, so that's not stored by the browser. And on the server side, you want to make sure that you're using OS security to protect sensitive data there. And then insecure storage. So, this is a laundry list of things that will go wrong, and we hear about this all the time with the various data breaches out there. Not encrypting critical data, not encrypting backups, storing keys insecurely. I mean, a lot of people seem to not have heard about these things called HSMs, hardware security modules, and so they're just storing all these sensitive keys on the file system right next to the private key, next to the public key, and it's just, the problem has been solved, but enough people are still not using the correct solutions. Poor sources of randomness or poor algorithms, inventing your own algorithm, we still see that, and if you do so, or even if you're using a well-known algorithm, failing to design the system so that it can easily handle key changes or other cryptographic maintenance procedures or revocation, things like that. So here, this is another screenshot from that web app pen test I mentioned. So in this case, I simply injected the command grep ir mysql dot. So it looked for the string MySQL in any of the files under the current folder, and sure enough, it found the MySQL username and password, which you may notice that it might be hard to read, but it says root. So they were using the MySQL root account, and it got even better because lo and behold, that same password that they used for the MySQL root account worked for SSH, for the system root account. So just with that one command, it was game over, essentially. So again, it's, why are we, there's multiple issues here, but it comes down to storing the password insecurely and reusing the same password across for two very different purposes. So how do we fix it? Only store data that you absolutely have to store. So for example, if your users typically don't have a lot of transactions, they maybe buy from you once or twice a year, you might actually be better off asking them to re-enter their credit card information each time instead of taking on the liability of storing thousands of credit cards on your servers. And you also, for any sensitive information that you're storing, or just in general, you don't want to allow any direct channels to the back-end servers. So you don't want to give people, you even want to limit this internally as much as possible. The developers obviously need access to the database to troubleshoot, but you want to make sure that that is screened off as much as possible so that only the people who need access to those systems can directly get to them. Everybody else has to go through the official system, which will have the audit trail and everything else that you can follow in case something happens. And we saw the screenshot earlier of the log data in the web server root. Don't store anything in the web server root that doesn't belong there, that's not intended for public consumption. Log files, debug, test code, unused frameworks, and just get rid of all that stuff. Only put production code in the web server root. And of course, don't roll your own crypto, but we already know that. So, wanted to take a couple of minutes to talk about kind of taking a step back and talk about what this means in terms of the broader security development lifecycle. So there's a lot of different things out there, a lot of different methodologies for securing the development lifecycle. So Microsoft has had their SDL for a long time, and they've, depending on who you ask, that has worked out pretty well for them. Certainly say that current Windows is more secure than previous versions of Windows. Cigital has these touch points, and I'll talk about that in a second, that basically let you focus on what are the activities that you should be incorporating into your development lifecycle, regardless of what methodology you're using. And then there's the OWASP CLASP, which is, again, designed to be a lightweight process that doesn't impose sort of a specific methodology. So a little bit more about the touch points. So the touch points are really a way to adapt security to whatever existing methodology you might be using. Because let's face it, there are a couple of subjects that are completely taboo with any developer: religion, politics, and development methodology. You don't mess with that. And so a lot of these methodologies that say you must do waterfall or you must do agile, they're not going to work because most organizations use some hybrid approach. They have their own methodology already in place, and they're not going to want to break that just to adopt a more secure way of doing things. So the touch points here are basically a way to say, okay, at which points in the process, and these boxes that you see at the bottom basically exist in any methodology. You're going to have requirements, you're going to have architecture and design, have a test plan. The one thing that every development effort produces is code, testing and test results, and then feedback from the field once it's deployed. And so, again, we want to start with our abuse cases. We want to think of the ways that the system can be abused. And then security requirements, we want to make sure that we're asking the right questions, as I mentioned before. And risk analysis. So we need to be thinking about what are the risks that our application has? What are the possible abuse cases there? And then as we're generating our test plans, we want to make sure that we're testing those risks that we identified, that we're developing test cases for that. And then once we're at the stage of generating code, we want to perform code review. And the key here is to do it as early in the process as possible. So once you've reached integration testing, or once you're close to going to production, that's almost too late, because in some cases that could be months or years from the time that you started developing the software, and a lot of the people who wrote the code may not be around anymore. So then you have the situation of trying to fix somebody else's code, and it's extremely, I mean, I go back, I look at my own code from 2 years ago, I can barely read it, much less somebody else's code. So it's very important to push that code review as early in the process as possible. And so one of the ways to do that is to basically give developers sort of a spell check tool that will catch a lot of the low-hanging fruit as soon as they check a new version into SVN or whatever repo they're using, and give them an idea of where those potential issues are. Now, from what we've seen, that's not quite as effective as looking at an integrated system and doing end-to-end testing, but it catches about 60 to 70% of the issues that you would later find. And it's much cheaper, much easier to fix those things early in the development process when the developer is still working on it, they're still around, they know the code, they just looked at it yesterday, so they know how to fix it tomorrow. And so that gives a lot more context for the developer. And the important thing is to do this inside of their IDE. You don't want to throw a 100-page PDF report at them and say, oh, you've got all these problems, all these SQL injection, cross-site scripting, go fix it. It's much better to provide them context-specific advice right in their familiar development environment. And so once we get to the testing stage, again, we're doing more risk analysis because now we're making sure we have everything covered, and we're coming up with more test cases, and we make sure that we're closing the feedback loop there. And then, of course, pen testing enters the arena. So, pen testing, a lot of times people see it kind of as the end-all, be-all. Oh yeah, we're gonna write the code, we're gonna test it, then we're gonna do a quick pen test, and then we're gonna roll it to production. Done. And really, the pen test is kind of a last resort. It's what did you miss? If you're building security into this process, what did you miss earlier in the process? It's a safeguard, basically. And then, of course, that continues on through deployment. You're going to do another pen test, repeated pen testing of the production system every year or whatever the requirements are, and then make sure that you're maintaining the system securely during your daily operations. And that you create things like security operations manuals that tell people the things that they should be watching out for as they're interacting with the system day to day. And so Besom is an initiative that Cigital started a couple of years ago that is fairly unique, because unlike a lot of models out there, it doesn't just kind of say, here's what we think you should do in terms of software security because we've spent a lot of time thinking about this and we've worked with quite a few people. It's actually based on real software security initiatives out there. And so you see all the names on the screen here. These are all participants, obviously some heavy hitters here. These are all participants in the Besom program, along with a lot of other companies. There's 51 total companies that are participating in Besom, and it's now in its fourth iteration. And there are 111 different measurements different parameters, different activities that it asks each of those participants about. And the unique thing there is that we ask them not, what do you think you should be doing in terms of application security? What are you planning on doing? But what are you doing today? And then we ask questions around how is it working? What are the metrics? And so forth, so that you can get a good idea of not only where you rank compared to your peers, but also what your next steps should be to improve your software security posture. So here's a quick overview. I mentioned the 111 measurements. They're divided into 4 domains: governance, intelligence, the touch points, and deployment. And you can see all these different activities that fall into those boxes. And for example, pen testing falls under deployment. We talked a lot about the touch points, the architecture analysis, the code review, and the security testing piece of it. And so basically the way to think of this is that if you're an organization and you want to find out what should I be doing to improve the state of my software security, here's a blueprint based on what 51 very well-respected companies are actually doing and have done in the past that has worked for them. So it's very much an empirical approach to it, and it lets you make sure that you're sort of keeping up with the state of the art. So in conclusion, I'm going to say this one more time, build security in. So you really have to think about security in your development lifecycle from day one. Bolt-on solutions don't work, and pen testing right before you go live is really just an exercise in futility, because you're never going to have time to fix all the things that you're going to find if that's the first time you're pen testing. So most developers are not incentivized for security. They are very much focused on implementing new functionality and features. And we really have to make sure that we're speaking their language when we're bridging the gap. We don't want to talk about exploits and vulnerabilities. We want to talk about bugs and fixes. And input validation is the root of all evil, really. It really is. I mean, if you can get good whitelist validation working, that quashes 70, 80% of what's out there in terms of ways that attackers can mess with your system. And output encoding is always going to be your fallback, because just in case you miss something, then you can make sure that it's sort of defanged when it gets output back to the user. So I'm getting the STFU sign, so let's take this offline. Thanks everybody for coming out. I appreciate the time.